Hello, S4 chemists. I hope you're all doing really well. It's Mr. Morton here, and today we're going to start Unit 3 of our National 5 Chemistry course. That's right, we've done Unit 1, we've done Unit 2, it's all up to Unit 3 now. First things first, in Unit 3 we're going to be looking at metals. Now, if you've looked at the periodic table before, you'll have realised that quite a lot of it is made up of metals. There's 118 different elements and 92 of them are metals. So the vast majority of our chemical elements are metals. So it's very important that we know them in and out in terms of properties, in terms of structure, in terms of reactions, and that's what we're going to explore in this topic. And today, really, in this video, we're going to want to set the scene for metals. I'm going to want to, as I said, go over their structure, something that we already know from Unit 1. We've seen these before. We want to talk about the properties of metals, what makes them useful, and finally we want to talk about, well, if we mix together different metals, we can make substances called alloys and have a little brief discussion about that. That will enable us then in the future to talk about reactions of metals and something called the redox reactions and look at different pages in our data booklet as well that we've not explored yet. So the structure of metals, as I've said, this is just revision. We talked about this in Unit 1 when we looked at bonding. Here we have the structure of some sort of metal. And I can tell this is a metal just by looking at this image. We have got these rows and columns of positive metal ions and they're arranged in a lattice. So there's the first point for the structure of a metal. It has a lattice, an important word, which essentially just means we've got like rows and columns. There's kind of order to it. Remember, this would be three-dimensional as well. It's just kind of tricky to draw. Maybe you can think of like a honeycomb to remind you of a lattice, or one of those like wee tasty potato waffle guys that you get. That's a lattice structure. Anyway, this is a lattice of positive metal ions. Which makes sense because, again, if we remember back to Unit 1, if we're thinking about in terms of ions, how do atoms become ions? Well, they either gain or lose electrons. We know that metals always lose electrons and always form positive ions. So the metallic structure is made up or comprised of this giant lattice of positive metal ions. Now, to form that positive metal ion, the metal atom has to lose an electron or lose electrons. So where are those electrons going to go? Well, here they are. Those electrons, once they've been lost from the atom, are free to move. They can travel wherever they want throughout this giant metal lattice. They've been effectively orphaned and they just roam around the streets of this metal lattice quite freely. We describe these free electrons as a sea, because there's lots of them, of delocalized, which just means they do not have a specific location. They can move wherever they want. So it's a sea of delocalized electrons. Now, if another, let's say, atom wanted to join this structure, then it would have to do the following things. It would have to lose its outer electron. So let's say I had a little lithium atom. Electron arrangement is 2, 1. There's its atomic structure, or excuse me, there's its electron arrangement as just an atom. For it to join this lattice club to add into the structure of this metal, what needs to happen is that outer electron has to be lost, has to come off, is removed. It joins this sea of delocalized electrons to roam around freely, and the lithium atom is therefore becomes a positive ion because it has lost this negative charge. Now we also need to appreciate the properties of metals and different metals, and they are all different. They're all different elements, so they're going to be slightly different even though they're all metals. Here's a couple of examples of some kind of common metals and some uses of them. Aluminium, obviously used for aluminium cans. Why would you use aluminium in an aluminium can? For a number of reasons. Because it's very light, it's not a very dense metal, it's easy to shape, it's very malleable, and it's also not toxic as well. So can safely contain food and drink without causing any damage. So there's loads of nice little properties there about aluminium. Mercury is one of only two elements that is liquid at room temperature, and it's the only metal that is liquid at room temperature. The other element is bromine, but that's a non-metal. So Mercury's got its own um, different properties compared to aluminium. Look at the melting and boiling points, much different. The densities are much different as well. And so therefore, just because we've got metals does not mean they're all the same. They've all got different properties. Same with gold and platinum. These are relatively unreactive elements, unreactive metals. They're both very good conductors of electricity, gold and platinum. Copper, again, different properties from all the rest of them. It's relatively easy to shape. That's why we put it into things like pipes, etc. that we've got here. It's also a very good conductor of heat. So in the kitchen setting, we'll have pans made out of copper to conduct all the heat from a stove, from the hob, etc. And here's a list of some properties of metals that we need to be able to appreciate. Density of the different metals. Each metal has a different density, and you can find information about the density of metals on page 7 of the data booklet. If something's got a high density, it means that the atoms within it are very compact. If it's got a low density, there's a lot of space in between the atoms. In terms of kind of remembering that, I think about like a bowling ball as being a very dense object. If I put a bowling ball in a swimming pool, it's going to sink because it's very, very dense. It's more dense than the water is. Whereas if I took something like a sponge, which is not very dense, that'll float on the surface of the water because it's less dense than the water. Conductivity, two types of conductivity, thermal or heat and electrical. As we know, metals conduct electricity because they've got that sea of delocalized electrons. Those electrons can flow and move throughout the metallic structure and carry a charge, carry electricity. So they're very good conductors of electricity. Their melting and boiling points generally are quite high. However, that is not a rule for all metals. Something like mercury has a low melting and boiling point, so does gallium. They have a range. That's probably the best way to describe their melting and boiling points. There's a range. Mostly high, but we can still see some metals that have a low melting point or boiling point as well. Strength, they're pretty strong. I mean, if you think about what we actually use metals for, we build bridges out of them, build buildings out of them. So they are strong. That structure of a metal, that lattice can be very strong, very durable. And the last two properties might be new words to you. Malleable means that they can be shaped easily. So think about the aluminium can, the tin, the gold ring. They are all shaped and can be quite easily manipulated and shaped into different shapes while still retaining their strength and structure. And ductile is a word to describe, I suppose, the production of wires, really. And what we think of when something is ductile is that it can be drawn out. I can pull out metals without just instantly snapping them. I can kind of pull and draw them out and make them into kind of long, wiry substances or wiry structures. The last thing to talk about in this video is alloys, or what an alloy is. Now, an alloy is simply when we take a metal and we mix it with another metal or another non-metal to, I suppose, to try and get the best properties out of the different metals that we're mixing. So alloys is, or are rather, an alloy is when we've taken a metal and mixing it with another metal. And sometimes we can mix them with non-metals as well, but it's mostly other metals. Now here's an example of a couple of alloys: solder, stainless steel, and bronze. We can think about each one independently and see why you would want to make an alloy. If we think about the solder, now solder is used to join together different pieces of metal. Think of like welding together two bits of metal. Solder is normally a mix of tin and lead, and while solders would be used, why would you want to use the alloy is it's got a relatively low melting point. It's actually quite easy to melt solder, which is useful because we need molten metal to connect and to kind of glue two different pieces of metal together. But when it's solid, it's pretty strong. So we're mixing together the relatively kind of low melting and boiling points of the metals used to make the alloy and the strength as well. Same with the case of stainless steel. Stainless steel, we're taking something like a metal like iron, which is a very strong, robust metal. However, it rusts very easily. So if we mix that with another metal that doesn't rust as easy, then we can kind of take the best of both worlds from those two different metals, and we can get a stainless steel which is both strong and doesn't react with the oxygen or water in the air and doesn't rust. And then with bronze, we can take some kind of, I suppose, precious metals which are expensive and can be hard to come by, and we're almost like bulking them up. So we could take some hard to find metals, something like gold or um, and bronze. The alloy bronze is normally a mixture of copper and some other kind of lesser metals like tin and nickel, and essentially we're trying to kind of replicate a precious metal. So instead of having to make coins out of gold and silver, we can kind of almost replicate that style and feel of a precious metal without the expense. So without having to use gold coins and silver all the time, we can use cheaper, more available metals to kind of facilitate this same use. So that's why you'd want to mix together different metals. You're trying to take the best of both worlds from the different properties and make an all-round better material.